All right, and last up we want to talk about some optical instruments that we can describe using our ray model and mirrors and lenses. And so we're going to start off with perhaps the most famous optical instrument, our eye, and or the eye. And specifically, we're going to talk about how images form at the retina. So this is sort of the screen of the eye. And the book goes into detail about a variety of different components of the eye. We are just going to focus on the lens and the retina or the screen, and we're going to talk about how you get an image to form. So the basic idea is you've got an object out in the world, rays from the object pass through the lens eye system, and the lens needs to be able to redirect those rays so that the rays come into focus back here at the retina. Now, one of the limitations or constraints that you have for your eye is that the distance between the retina and the lens is fixed. So you can't shift or move the lens around. Rather, what you do with the eye is you change the focal length of the lens. And you do that by a few different ways to do that, but the primary way is that these muscles here connected to the lens can stretch or compress the fluid in the lens so that you get a shorter or longer focal length depending on the object that you're looking at. And of course, the amount of stretching compression is limited, right? There's not an infinite amount of stretching or compressing that can be done, and so your eye has limitations. And in fact, many of us know, myself included, that there are some common ways in which your eye can fail to bring images into focus. The first way that can happen is that your lens, the lens in your eye can be too strong. That is, when you have really far away objects and the lens isn't able to lengthen enough, the focal length isn't able to be long enough, the rays will come into focus in front of the retina here. Right, so you need the rays to converge more slowly, but for whatever reason, the lens in your eye isn't able to adjust, and so things will come into focus before the retina, and so when the rays hit the retina, things will be blurry because rays from the same spot on the object are hitting different locations on your retina. Right. The other way that this can happen is if maybe your lens has a typical range of focal lengths that can be achieved, but for whatever reason, the eyeball is a little bit longer, and so you don't have a corresponding focal length that will reach the back of the eye, will reach the retina when you're looking at things that are far away. And so this is called myopia. The converse of that is if your lens is too weak or your eye is too short. And in this case, the rays will come into focus beyond the retina. And so could be because the lens just isn't able to produce a short enough focal length that will bring the rays to converge in time. And so when the rays hit the retina, they are going to be hitting different locations. So those rays should be coming from the same spot on the object, and so they hit different locations for your retina, and so you're going to have a blurry image. And the same thing happens if your eye is just physically too short to match the focal length of the lens. And so this is called hyperopia. And so for myopia, you probably know it better as being nearsighted. That is, you can see things up close just fine, but when you go to view things that are far away, again, your lens is too strong for those far away objects, and the rays converge too soon and don't hit the retina until post-convergence, and so you'll have a blurry image. And so what you need to do to correct that issue is you need to put a diverging lens in front of your eye so that the rays that are reaching the lens, rather than being parallel, they're actually diverging slightly when they hit the lens or the eye system. And that divergence, very slight, allows for the rays to now come into focus back here at the retina rather than up here originally, where things would be out of focus when the rays reach the retina. And so when you're nearsighted, right, you can see things up close but not far away, you need a diverging lens placed in front of your eye so that you can correct for that to see things that are, in effect, infinitely far away, things that are far away. Now, if you are farsighted, that means you can see things that are far away, crisp and clear, but when things get close, you are unable to bring those images of those objects into focus. And again, rays that are unaltered reach your eye and come to focus beyond the retina. And so what you need to do is you need to introduce an optical element, a lens, that causes the rays to converge faster than what your eye can accomplish. And the way you do that is by putting a converging lens in front of your eye. And so for hyperopia, placing a converging lens in front of the eye corrects the issue. For myopia, placing a diverging lens in front of the eye. All right, the next instrument is, again, very common, the camera. And there are, a large variety, a large number of cameras and design elements that can be discussed for a camera. And so we're not going to get into the details. We're just going to talk about the typical difference between a camera and your eye. And the typical difference is summed up in this statement down here. That for a camera, you're actually able to move the lens, unlike in the eye. And so to bring things into focus, different objects, the images of those objects into focus that are different distances away, you vary the distance between the screen and the lens as opposed to changing the focal length of the lens. And so, again, there's a lot of ways that you can actually implement this in a camera. We've got a picture here of a more common sort of modern camera that has, for a detector, a CCD, basically similar to your cell phone camera as opposed to film. And so the basic takeaway here for the camera is that you can vary the distance between the lens and the screen, whereas in the eye, you're varying the focal length of the lens. Another very common instrument is the magnifying lens, and the magnifying lens is essentially what we've been talking about with converging lenses for the thin lens section. It's just a specific application of a signal magnifying lens, or a single converging lens. And so when we talk about a magnifying lens, what we want to talk about is something called angular magnification. And so rather than the linear magnification that we've been talking about in the thin lens equation, we want to talk about angular magnification, which corresponds to the apparent size of an object when you look at the object. And so it doesn't correspond to the physical size, but corresponds to the amount of sky, me being an astronomer, or the amount of your field of view that is taken up by the object. And so the idea of angular size is that how far away a physical object is from you will impact the angular size of an object. So pick up anything at your desk or wherever you are and hold it out at arm's length and look at it and then bring it closer. What you'll see is that the object appears bigger as you move it closer. The angular size of the object is getting larger, and that's because the physical size stays the same, but the distance to the object is getting smaller. And so it's angular magnification that we care about here. And so the general principle for a magnifying lens is that, right, all eyes have limitations. So the first thing you would do to look at an object is bring it as close to your eye as you can without it becoming blurry, and this is known as the near point of the eye, and the typical near point for an adult is around 25 centimeters. And so if you bring the object 25 centimeters from your eye, that's essentially the largest angular size you can get without any additional lenses helping you out. And so from that initial object being 25 centimeters away, then what you're going to do is you're going to place a converging lens in between your eye and the object. And what you want to do is you want to get the focal length of the converging lens so that the object is located just inside the focal length of the lens. And the reason you want to do that is because the rays that pass through the lens, notice how they're diverging on the right-hand side. And so what that means, your eye is going to trace them back, and there is going to be a virtual image produced, angular size larger than the original angular size of the object. And so by placing a converging lens so that the focal length of the lens is just beyond the location of the object, you will get a magnifying lens. And so the book works out the geometry to show that this is the expression for a magnifying lens, the angular magnification of a magnifying lens. And when the distance L here is set as the near point, and little l, that's the distance to the eye, from the eye to the lens, is 0, so basically you place the magnifying lens very close to your eyeball, then these are the two expressions for magnification. So if the image that's formed is close to the near point, you get the top expression right here. And if the image that forms is out at infinity, you get this expression. So basically it just depends on where exactly the object is placed relative to the focal length of the lens. And so the point, I suppose, of these two expressions is that they're nearly the same, 25 centimeters over the focal length of your lens. And if you're viewing the image out at infinity, so that's where your eye can be the most relaxed, then you get a magnification of 25 centimeters over the focal length. And by straining your eye a little bit, you only increase the magnification by 1. So whatever the magnification is in the L equals infinity case, add 1 to that, and that's the maximum magnification that you can possibly get. And so typically what I work with when I'm using a magnifying lens is I work with this expression for the angular magnification. All right, our last two instruments are instruments that take advantage of multiple lenses or perhaps even mirrors. The first one is the microscope, and the basic premise of a microscope is that you've got an object that you can physically bring your lenses very close to. And so the idea behind the microscope is that you place your lens system very close to the object, right? And so for a microscope, or for any compound lens system, you treat the lenses essentially separately. So the typical language that gets used for a microscope is that this first lens here is the objective. That's the lens that's closest to the object. And then the second lens is the eyepiece. That's what you look through. And so the basic idea is that the first lens, the objective, the object is placed outside the focal length of that lens. And so you get an image to form on the opposite side of the lens, and notice that that image is inverted from the original object. And so this is a real image. And so for the microscope, that first objective lens produces a real image. And then this real image gets used as the object for your next lens, your eyepiece. And you'll notice that the object here is inside the focal length of the eyepiece, this converging lens. That means we're going to have a magnifying lens. And so the eyepiece is effectively a magnifying lens, which is magnifying the image that's produced from the first objective lens. Right? So if you're doing ray tracing, you would ray trace through the first lens and get the image formed from the first lens. And then you would use that image as your object for your next lens. And so this is the final image that gets formed as a result of two different lenses bending the rays that are passing through the instrument. So if you want to talk about the net magnification of something like a microscope, these multiple lens systems, you've got to take into account both the linear magnification that happens from the objective lens and the angular magnification that happens from the eyepiece. So the basic principles here, for a microscope, the object's going to be very close to the focal point of the objective lens, just beyond it. So you get a real image formed from that objective. And then from the objective, you get a real image. The eyepiece, which acts as a magnifying lens, gives rise to this final image. And so the book goes through quite a bit of algebra and a variety of different geometric and algebraic relationships to come up with the expression for the linear magnification and the angular magnification. And so I'm simplifying a little bit here. So if you look in the book, you'll see a lot more work done than what I'm providing here. The first thing that I'm going to do is I am going to mention that often in microscopes there is something known as the tube length L, which is defined as the difference between, if you look up here at this picture, the difference between this distance di and this distance, the objective focal length. And so that is, for most microscopes, as I understand it, often set at 16 centimeters. And so linear magnification from the objective, if we remember the definition for magnification, image distance over object distance, using the thin lens equation, that becomes this. And again, the tube length is defined as di minus the focal length of the objective. So the linear magnification of the objective is the tube length divided by whatever the objective focal length is. And again, often that tube length is 16 centimeters for a microscope. Now, the eyepiece, well, again, we just went over the eyepiece, or went over the magnifying lens. So the angular magnification of the magnifying lens, to simplify, is just 25 centimeters over the focal length of the eyepiece. So if you want to get the net magnification of a microscope, then you just multiply those two together. And when you multiply those two together, you end up getting a factor of 16 centimeters over the focal length of the objective. So that's the linear magnification. And then you multiply that by however much angular magnification happens. That's the 25 centimeter over the eyepiece focal length. And so this is a quick way to get the rough estimate for the total magnification of your microscope, essentially just combining the information you have about the eyepiece and the objective focal lengths. All right, and last we have, of course, my favorite optical instrument, the telescope. And the basic premise for the telescope I have written down here is that for a telescope, the object is infinitely far away. It's very far away from the objective. And so the simplest form of a telescope combines two lenses, and you sort of have two versions of this. You can either have a converging lens as your objective and then a diverging lens as your eyepiece, or you can have a converging lens for your objective and then another converging lens as your eyepiece. We're going to focus on this one in just a minute, but we'll mention that this was sort of the original telescope that Galileo used to study the sun, to study Jupiter, and the advantage to this telescope is that the final image that forms is an upright image. And so what Galileo did was he basically took the already existing spyglass and basically pointed it to the sky. And the spyglass was used for shipping and on ships to essentially view off onto the horizon to see what ships were coming into port. And so having the image upright rather than inverted was a useful thing for the spyglass. And again, Galileo used this spyglass as his telescope. But we're going to focus on this version of the telescope, which combines two converging lenses. And so the basic premise for this telescope is that the objective is used to form a real image, and the real image is going to form, since the object is infinitely far away, very far away, then the image formed by the objective is going to be at the focal length of the objective lens. And then what we're going to do is we're going to take this image that's formed and we're going to use that as our object for our eyepiece. And our eyepiece is a converging lens, and we're going to choose the converging lens or move it around such that the object is just inside the focal length of the eyepiece, giving rise to a magnifying lens. And this is what's going to give rise to our final image. Now, you'll notice our final image here is inverted, so you may be tempted to say that this image is a real image, but that's not the case. The first image that forms is real. That is the inverted image. And then from this inverted image, which we use as our object, we get a virtual inverted image. And so it is possible to have a virtual inverted image if you have multiple lenses in your ray path length. So when we talk about telescopes, what we care about is the net magnification, the overall magnification, and this is angular magnification. So this is comparing the angular size of the image formed after all of the refractions or reflections. Compare that to the angular size of the object originally. And so looking down here at the picture, we can look at both the angular size of the object originally and the angular size of the image afterwards. And we'll do that just by looking at some triangles. And so first, I've got this ray from the object passing through the center of my objective lens, and so that ray just continues on. And so that means the angular size of the object, which is this angle right here, right? That's the same angle as this over here. the angular size there is going to be the height of the image that's formed divided by the image distance, which is the objective focal length. So normally you might write, tangent theta of the object is equal to the height divided by the focal length of the objective. But since this object is really far away, that angle is going to be very small. So that's the small angle approximation, that the object angular size is h over the objective focal length. And so that's what I've got written over here. I added a negative sign here, just corresponding to the fact that the image is forming above the optical axis, and the object was originally below the optical axis. Right? So that's somewhere I've got to include a negative sign to take into account that the image has been that the image is inverted. So the next step is to look at the angular size of the image. Well, so the angular size of the image is going to be, well, here we would just trace this ray along that line. So what's that angle? Well, that angle, if you zoom in, is just the height divided by the object distance to the eyepiece, which again is the focal length of the eyepiece. So again, you might write tangent theta eyepiece equals h over focal length of the eyepiece, which again, small angle approximation, is just theta of the eyepiece. Or theta of the image is what I'm using. And so now I can just plug both of those in, the h's cancel, and I end up getting that the net magnification for this simple telescope is just the ratio of the objective eyepiece to the objective lens to the eyepiece lens. So f objective divided by f eyepiece. And so this tells you that if you want the largest overall magnification for your telescope, you want a long objective focal length and you want a short eyepiece focal length. And so to give you a sense of what that means in practice, this is one of the largest, I think is the largest refracting telescope ever built. This is 62 feet in length, I believe. And the point for if you want large angular magnification, you need a long objective. Since these are lenses, that means you need a really long tube. You need to take up a lot of space, right? And so one way that you can avoid this issue, if you want the magnification but you don't want to take up the space, is you can switch from lenses to mirrors, or to mirrors actually. And so this is one of several reasons why all research telescopes now are reflecting telescopes as opposed to refracting telescopes. The other main reason for that is that the size of the telescopes is getting so large that it was difficult to support a large lens. And with a mirror, you can put a support underneath or behind the glass reflective coating, right? So you don't need it to be completely open to let the light pass through. And so these are just two of many ways that you can leverage spherical or parabolic mirrors to reflect light so that you can have long objective focal lengths without taking up large amount of physical space. And of course, since this is part of my job, I need to mention my favorite telescope, the Hubble Space Telescope, which is a reflecting telescope, 2.4 meter in diameter, so that's the aperture, the opening. The primary mirror, the objective mirror, is 2.4 meters, and this is a telescope that's in low Earth orbit, was placed in low Earth orbit so that the telescope could observe not just visible light, but also near infrared and also ultraviolet. Ultraviolet capability is really the thing that set the Hubble Space Telescope apart. Why does a UV ultraviolet telescope have to be in orbit? Well, because the Earth's atmosphere, which does great at keeping us alive, does poorly at letting observers observe the ultraviolet